Jill.
Oh, nice to meet you, Mohammad.
So I guess we're
Yeah,
nice to meet you.
Hey, good to
How's
meet
it
you.
going on, Warren? Nice to meet you.
Oh, no worries.
Nice to meet you.
Nice to meet you.
How's it going?
Good evening, everyone. I know we're getting started a bit late, so I'll go ahead and skip through that, like this part really quickly, then I'll hand it over. So thank you for coming to today's talk. Obviously, I would say this one is going to be, I'm going to hopefully find very interesting. Dealing with cutting size is one of the things I have to deal with on a daily basis. So quick welcome back to the Washington Post. To our virtual guests, you are muted for now. During the talk, I think generally please just try to drop questions in the chat and I'll try to catch them as I can, but at the end we'll have a little more of an open Q&A. And obviously, as you've heard, we are recording. So without further ado, I will go ahead and hand it over.
This is, in a sense, the second time I'm in this meetup. The first time it was 7 or 8 years ago. I came to this the Capital One meetup. Back in that time, I barely knew anything about iOS. I was learning Objective-C. I barely knew anything about auto layout, nothing. And a little bit about myself. Apparently, my name is Mohammad Faani, and about things I'm curious. And if you see on the left, some of the things I've been recently curious about is optimizing binaries and what's the difference between an app bundle and the binary itself. Today, the thing that started all this journey of mine was this command that you see here. Two of my colleagues, they saw an opportunity with XE frameworks, and they were optimistic that if they use XE frameworks, then we can cut down on our build time for our app. And they transitioned over some of our frameworks to XE frameworks, and they were able to cut down on the full release of our app by a couple minutes. This was significant, but on the downside, we saw some increase in our app size. And my colleagues, they tried to work on it, and the task got carried over. I got assigned to it, and I started looking at this, and I've never touched Xcode build. I don't know what this skip install means. I don't know what this build library for distribution means. I don't even know what a precompiled binary is or what XE framework is. I had a lot of questions for myself. Like, what's an archive? What's inside it? How do you create one? What's an XE framework? What's a precompiled binary? How do we create it? How does this impact app size? Which build settings in Xcode are important? What role does CocoaPods have in this? Does static and dynamic linking have a role in this? When does something get compiled? Do we do that in the pods repo or in the host app repo? Does static versus a dynamic library linking again have a role in this? How can I inspect the binary? In the final product, where does the framework go? What's app thinning? How can I include DSIMs and not impact the app size? What are some of Apple resources in all of this? And is there anything that I just don't know that I need to know? So a lot of things. And this was sort of like the state that I had in my mind. And we're going to see this another 20 more times. We're not going to see anymore. And so I had some serious issues. This was the brain scan. It was really red. A lot of problems with me. So 2-3 weeks passed, and I started to get on some WBC videos. And that's why I'm here. I'm here to share some of the finds that I've had. So the agenda for today is some jargon and anatomy. We're going to figure out how we create a binary. We're going to do a Swift C demo, which is a Swift compiler demo. We're going to do some build directory inspection. We're going to do some inspection on the binaries themselves. We're going to talk about symbols. And then we're going to segue into how we can have some X-ray vision and do some surgeries using some tools, NM, strip, OTool, file, DYLD info. So first and foremost, how do you create a binary? Well, first we have to understand what a binary is. We're already using them every day. Like if you're using LS in your terminal, that's a binary. If you're using CP, that's another binary. They don't have a file extension, and they get created as the end product of linking all your source codes together. Things you link are either your own code or dependencies. The dependencies could come in the form of source file or precompiled. So super high level, you have source code, then you compile it, you have object code, and then you link them together and you have your product. So if you have 10 files, then you have, that means after you compile them, you're going to have 10 object files. Once you link them together, you're going to have a single target, a single product. So you might be asking, what is an object file? It's in binary format, still zeros and ones. It might reference some undefined symbols. So for example, in this person.swift file, if I compile this, if I want to compile this, well, it's going to be like this address type is undefined. So once I compile this object file is going to declare itself like there's something missing in me. I need to find that. They're useless by themselves. Everything is much like a piece of a puzzle. A single piece of a puzzle, if you look at it, it's useless. But once that you connect them all together, you link them all together, you stitch them together, you have this final product. They're suffixed with O, that's why they're called object file. And the reason that they're called object file is because they're the goal, the results that you're aiming for. Your source code, in a sense, is considered to be your subject code. And they're intermediate because you really don't need them. Once you compile it, once you produce your product, they're gone. You don't need them. So yeah, piece of the puzzles here. So what's inside an object file? Symbol names, compiled code, constant data, imports. Like in the previous example, address was an import for the person object file. Exports, if you have something that you want others to use, then if you set the correct access modifier, then other files can use that. If you don't set the correct access modifier, then it's not going to be presented. Other object files that depend on it can't use it. You're going to have a compiler or linker error. And they also contain some dwarf information. So repeating that diagram before, with only this addition that object code and product, they're both machine code. They're both zeros and ones, with the only difference that this is stitched together, this is single pieces. So this is from the WBC talk. Each file gets compiled into its own object file. Then you link them all together, and then you create your binary. So let's go and demo this. So to ls, let me just remove this main binary. Okay. So I have this. Oh, I'm not sharing. All right, so I have this. Let me increase the font size a bit. Okay, so ls, I have only main.swift here. Now let me show what's inside of it. All it does is it takes some arguments. The first argument, so we're going to use it as the first name and the second argument as last name, and we just print greetings. So to compile this, I'm going to use Swift C, and then I'm just going to do main.swift. Now I'm going to do ls again, and now you see I have the binary there. So how do I use it? I just do main, and then I'm going to do Scott. I'm sorry, I already forgot your last name.
It's right there in the Zoom chat. Just put L.
L. Okay. All right. So greetings, got L. So we have that. All right. So that's what Swift C can do. It's a Swift compiler. You cannot compile Objective-C or C or C++ with this compiler. It's only for Swift. If you want to compile Objective-C code, then you have to use Clang. Clang is for the C family class, C family language. So to show you a little bit more further what's happening here, I'm going to do -V. I'm going to do again the same thing. Now, this time you see you see everything that's happening under the hood. So the thing that it's important for us is this object file that's getting created here. Main, I don't know why it's a suffix with 1, but we created our object file. And then using LD, the linker, LD is the linker, we link this object file with all the rest of the libraries and SDKs. And then at the end, we create this main binary. I can do one more thing here, swiftc -g. I'm going to do again verbose. Can anybody guess what -g is for? Debug information. So now at the end, I'm also producing this main.dsym. And we produce that using this dsym util. So if I do ls again, now I have my main dsym as well and main here. Now you might be wondering, like, how is this related to what we're doing in Xcode? And the answer to that question is what I just showed here, what we just saw here is a very small manifestation of what Xcode does at scale. Xcode doesn't have a single file. It has maybe 20,000 files. It doesn't have like 5 libraries. Maybe it has 25, 200 libraries that it depends on. So it takes more time and there's more instructions that are passed on to it. I can also do, let me just open this here. Well, I'm not going to open it. I'm going to do just ls-la here. And then you can see that the file size is 53 kilobytes. Okay. Now, let me just remove everything except for all right, so we have this now. I'm going to compile this one more time. Oops. All right, I'm going to do ls-la again, and it's 52 kilobytes, okay? So last time the size was slightly different because we had to mention, we had to ask it to include the debug symbols. So there's a cost that occurs from including those debug symbols. Now, one other thing that affects the size as well is the optimization. So if I do swiftc again, and I'm going to pass O for optimize, main.swift again. This time it's smaller. Again, Xcode has something similar to this as well. So let's move back to the slides. Let me share my slides again. All right, so a quick recap of what we just discussed. swiftc is the compiler, LD is the linker, and then dsym util is a linker specifically for debug information. Clang is for the C family language. Now, let's move on to some linker history. The way that this works at the high level, you have 2 types of linking. One is static linking, and the other kind is dynamic linking. If you struggle to understand like the differences between static library and dynamic library, the better way to think about it is to think about how linking works. Ignore the fact that they're a library, but focus on the fact that you need to link things. So this diagram, it was inspired by this user Axio Dablo from Stack Overflow with some modifications. So you have this main.swift, you compile it, you have your object code. Then you might have a static library, which is auth.a, stands for archive. And once you link with this, it's static. What this means by static is you want the linking will happen at build time. So once this is linked, then there's not a separate binary that exists in your app bundle for this auth .a library. Now, if we do this for dynamic library, now this we just renamed it to core.framework. Once you want to link this, the linking is deferred to the time that the app is getting launched. So that a dynamic library will be its own separate binary. There are some benefits. There are some pros and cons to this, which we'll discuss in a bit. So with static library, the linker knows the static library, the idea is link now with the promise and the actual implementation. With dynamic library, it's link now with the promise or the headers, load the actual implementation upon app launch. So if you're deferring this to app launch, then this means your app launch could be slightly slower. If you are doing all the linking during build, and this means your build is slower if you do it with static linking. So now let's go on to a project demo. Let me stop sharing again and share my project here. Perhaps I should share my screen. All right. So we have this project here. The project structure is if there's a workspace and I have this cool application. And if I go, and then this other core, this is a framework. This is a static library. Okay, so if you look at these settings here, the settings are actually different between a static library and a framework. So see here, you have like all these build phases and build setting, extra signing. Because it's own separate binary, there are more settings that are associated with it. Now, back to my cool app here. If I go into this target here, down here, you see they're both linked, okay? If I go into my content view, I've imported both of them and I'm just running them both. And once they're ran, this is what we get. We're authorized, which is just what this function is logging, and iPhone 14 Pro, which is what we're printing here. So what's interesting about this is if I go into this auth here, if I search for Mako, you would see that this is the type of this is specified as a static library. If I go for this framework, the type of this is specified as dynamic library. If I go for my main app, again, the type of this is specified as an executable. So that's a build setting, but let me go and show you in derived data what we have as well. So this is the derived data of that project itself. So let me actually just go up. So from the build folder, products, debug, and from debug build, we have this folder. Now, if you see here, it's much like the process is the Xcode will first lay down each library for you, like it was put on a table. Okay, I have my libauth. Okay, I have my core.framework. Okay, and I have this app wrapper. Now, once I have everything laid on the table, I'm going to stuff them into this app bundle, app directory. So if I open this, if I right click on this and do show package content, we're going to see this. Let me just increase the fonts. Okay, a bit. We're going to see this. Now, you might be wondering, okay, so how everything is ultimately built. So we have this cool binary, and it's associated with this cool app bundle. Now, if I go into the frameworks here, we only see core.framework. But what happened to the libauth static library? What happened to it was that the linking happened during build time. So any symbols, any anything that you declare is not part of this binary. But with core.framework, it's its own separate binary. That's why you have those extra Xcode settings and configuration for it. Right, so moving back to the slides again. So where this could get blurry a little bit is, I think we already covered it, but like if you go into your builds directory, this is what you're going to see at the high level: core.framework, libauth, and then cool app. And within the cool app, you're going to have your info plist, your frameworks, your assets, provisioning profile, storyboards, localization, all of that. Then under your frameworks, you're going to have your every dynamic library, and then under that, it's going to have its own binary as well. So that's that association, but libauth is just absorbed into the cool apps binary itself. We already talked about this. I'm just going to move on. So a bit of a deeper dive here of everything that we just discussed. Everything that you want to, any library that you want to include, it has to be part of the search path so that it could get linked and compiled with. So on my computer, if I do like which ls, it'll show me that this is where it's located, because that's how it works. If I do echo path, it will list all of the paths that I have so I can run and execute from. So it's a safety measure. You have to sort of like do the same thing when you're trying to build and compile your apps. So from here on, I'm just going to like try to answer some of the questions that I had myself about like, where do we draw the line between compiler and linker a little bit? So when does the compiler stop working? Well, it stops when there's nothing left to compile. What does the compiler do? It does some pre-processing, syntax validation, validate the implementation, which means like if I need to return a string, then if that's declared in the function signature, then my return statement should be a string as well. And it also looks for matching headers. Like if if I have a person's structure class, and it depends on an address object, and then that address object expects a city, then it has to match with the address object file needs to declare that as part of its things that it has available to the person object file. What does the compiler create? It creates an object file for each file. Now, those are the questions that we answered about compiler, but when does a linker finish? It's slightly different. It doesn't go through everything. It just starts from main, and it's going to go in main. It's going to be like, okay, I see some undefined symbols. Let me go and see if I can find them. And then it finds those symbols, and then those symbols are going to depend on something else. So it's going to have to keep going and going and going until it resolves everything. Now, something that I thought originally when I was like doing development was like, if we have dead code in our application, then what's going to happen? Well, the compiler is sort of smart. It does this selective loading, and if something is not to be used, it's not used at all, it won't load it into your app binary. So linking stops when you finish when you stop finding undefined symbols. If you have some undefined symbols, and then the linker will error out. Some other questions. Compiler parses all the files as we discussed. Linker only parses the files that it needs. Compilation can be done in parallel. Compilation obviously is done first. The compiler doesn't generate the executable. That's the role of the linker. Linker does that. It sort of like relates all the dilibs, object files, archives, frameworks, all of them together and creates your framework or executable. So the inputs for the compiler are like source code. The inputs for the linker are object files and libraries. Another thing that also was interesting for me to know is, as we said, the linker creates the binaries and dilibs, but it doesn't create the app, the .app. So Xcode creates that .app or .framework with a certain structure. Like it creates a directory and then puts your app's main executable in them, and then the info plist, the frameworks directory, all of that. And if you go into Xcode, like right now, if I go to Xcode, well, let me do that after I'm done with the slides. But if I go into Xcode and I search in the report navigator, I will see each and every one of these steps. I will see that Xcode is doing this. It's creating this directory. I will see that it will copy frameworks into the directory. I will see that it will like copy the localization provisioning file, all of them. Assets, fonts, all of that. There are some benefits that we discussed. We discussed this, we discussed that too. Another question that I had for myself was like, does compiling happen on the device? No, it only happens on Xcode. The format, just sort of discussed this already. And the location of that static library, it's within the app binary, already discussed. Dynamic library, it's separate from the main binary. But essentially, both of them get absorbed in the app wrapper, just into different locations and different forms. Now, you might be also wondering, like, why do we have both of these ways? Well, one of the advantages that dynamic linking offers is sharing. So for example, if I have my app and then I have like 4 app extensions with dynamic library, because the dynamic library sits outside of the executable, away from the executable, it can be shared with any number of binaries itself. That's why dynamic library wins here. Apple can also do something more special. Imagine if you have like 5 different apps and they're sandboxed, right? So, and you want to, across these 5 different apps, you want to make network calls. What's going to happen in that situation? It's not going to be like the OS is going to spin off multiple like processes that handle networking. No, it's going to have only one process that handles your networking for you. It gets shared across different apps. Only Apple can do that. For the reason of that is security, and because it wants to do sandboxing. Like imagine if, for example, Facebook, the Facebook app and the Messenger app, they're completely sandboxed. Imagine if they had like cross sharing between them. That's some sort of like a security issue, even though they're from the same company. The only sharing that can happen from us developers is just between an app and its app extension. The other thing that Apple is special is right now we publish our app to the App Store and we build it with UIKit, which is from iOS 16 version. Now, as soon as iOS 17 comes out, do we need to recompile our app again and submit? No, because everything that is about UIKit is a dynamic framework, and Apple can load it into their OS and we can just start using it. So that's again another beauty of this. But then again, this is special because Apple can only do this. We can't load in dynamic libraries into our apps after we submitted them to the App Store. And apps become faster because if app A is already making network requests and app B comes into the memory, it doesn't need to load in that networking library. It's already on the memory. It can just start using it immediately. Now, this is where it gets interesting, and this is where like debug symbols is probably at the heart of my discussion here, and DSIMs. So dilibs, because they're separate binaries, they need to have their own separate DSIM. Static libraries, they get linked into the main executable. So if there's any DSIM associated with them, they have to get absorbed into the main executable's DSIMs as well. So we sort of already answered this. I'm gonna skip this one. All right, so about size, dynamic linking helps with resharing. Static linking helps with selected loading. So both of them, in some ways, they help us to reduce the app size. So think for a second. If I'm dynamically linking a library that's 10 megabytes to one app and 2 app extensions, how much have I increased my app size? 30 or 10? The answer is we've increased our app size by only 10 megabytes because they can get shared. If I have to share a static library with 1 app and 2 app extensions, then the answer depends. It's because with static linking, you know already during compile time which symbols are getting used, so you can select them. And that's also another difference. That's one of the advantages of static library. Like dynamic library, you can't do that. Apple's recommendation based on their WWDC video is that you should try it out. Don't immediately jump to one another. Usually speed is not a major consideration. The more important consideration is usually size that you should be considered of. So it just depends. All right, so mini recap of what we just discussed. We actually didn't discuss dependency graph, but what that means is on Xcode, once you like configure your project, and based on your build settings, Xcode is going to be like, okay, this target depends on that target. This file depends on that other file. That's your dependency graph. So you could, once you do that dependency graph, then you create the framework bundle, which is just creating an empty directory. Then you compile and create all your object files. Then you link and create your binary, and you create your DSIMs afterwards. The app build process is more or less the same, with the difference of now you copy frameworks and other files into your frameworks directory, and you have your localizations, you have your fonts as well, and so on and so on. You create your DSIMs, then you do stripping, then you do signing and archiving. So how does this all matter? Well, it affects the app size because we want to know where to look for and how to look for it. We haven't exactly answered the question of like how to look for that, but O2 is one object, and it is another, DYLD info is another. DYLD is a dynamic linker, LD is a linker. This also affects app launch, which we discussed. If anybody's more interested in that, they can just go and there's a WWDC talk about app launch, look into that. Now, I have this slide up here, debugging and symbolicating. And you might be like, how does this matter? How does this matter to like app size? And well, the reason that it matters is part of our build process. The part of our build process is active development and debugging things. And to debug things, Xcode has to build a lot extra information for you to be able to debug things. That extra information comes with a cost, and that cost is size. So how do we debug things in Xcode? Well, you need a debugger that uses simple information. And simple information, we mean dwarf. What does dwarf contain? It contains type, function, and variable names, file name and file number, mapping between symbols and their addresses. And also, the debugger can do the following: breakpoints, stepping into and out, expression evaluation, and it can do graph tracing for you. So if you ever wanted to test your app with like, how does it work without debugging? Well, you just set this flag to false. And then if you go and set a breakpoint on anything, Xcode will throw you this warning and say, Xcode won't pause at this breakpoint because it has not been resolved. And so this code from Futurama, when you do things right, people won't be sure you've done anything at all. That's how I felt about Apple engineers all this time. Like they like have built a system that we've never cared about, like how the debugging works, but there's so much consideration that's been put into that. All right, so now we're going into discuss about the inspection and how you can inspect your binaries. So there are different ways of doing that. You can go through the sample app, just as we did in the beginning in terminal, and just try to see like what commands are getting ran and what flags are being passed. Like if you're creating debug information, then that's something to be considered of because it affects your app size. You can go into look into your build logs. I will show that towards the end. You can inspect app wrappers, and then you can also inspect binaries. We're going to show that. We already showed how you can inspect app wrappers. You can also pinch to zoom, but that really doesn't do anything for you. You can also get physical, but again, that's not helpful either. So our focus is on, from now here on, is on inspecting binaries. So the commands that you want to look for, we already showed you this sequence. The commands that you want to look for are Swift funren, which does the compilation, LD, clang, which does the compilation for non-Swift files, dsym-util, which does creates the dsym for you, stripping, and this is key, this is really important. So OTool, you can use this command for figuring out the dependencies of your module. NM, which stands for names of your symbols. It'll give you a lot of information about things that you import or export or functions that you have internally yourself. So what kinds of symbols can we have and why do we have them? Well, for cross-binary communication, like your app has another binary and how do you communicate between those two? The symbols are your way of communicating between them. And also for debugging information. If you don't create these debugging information, then your debugger won't work as well. The type of symbols, global, debug, local, undefined symbols, basically are your dependencies, and some other kinds of symbols. So at the very high level, you compile, and then you link all your debug info into the dsym. And after that, what you have to do is you have to strip your app from the debug information. This is with some oversimplification, but at the high level, that's how it works. If you don't strip your app, then you're shipping your app into the App Store with a lot of extra bloat. So let me stop sharing again, go into my terminal. Oops. It's already sharing everything. All right, so let me just remove everything that extra that we've had. Let me. Do I not have it? Okay, I don't have it. Okay. Okay, so we're going to compile one more time. Swift C main.swift. Now this is where the fun part comes. So now we're going to use NM. I'm going to do NM, names of the symbols, -a, main. That's everything, all the symbols in my greeter binary. Now I can make this slightly better worded and I can do xc run swift demangle. Okay, now they're slightly more readable, human readable for us. Okay, now if you're ever interested in like what this NM and all that does, then just go and look into here. And like it sort of like lists everything here for you, like display only undefined symbols or display only like global symbols and so on. So that's one thing that we can see here now. So let me just do that, and then I'm going to do get a line count. So we have 46 symbols. Now if I do strip stx main, do that again. Now I have 35 symbols. By stripping, you reduce your app size. Now let's just try this one more time. Swift C -g main.swift. Now let's see, 87. So now we have an increased symbol presence in our binary. Now if I strip this again, back to 35. If you don't do that, you're leaving bloat in your application. Now I can also, just to show you like more stuff here, like I can pass an M, and then this sort of like passes this, it mentions the library that it was originated from. Like, so this is all from lib swift core, all them lib swift objective C. I'm trying to find symbols from our own module. Not seeing him, okay. But yes, so that's something that you want to do. Now, the other thing was, yes, O-tool. So O-tool, I can do also this O2-L, I can do main. And then this will list all your dependencies of this binary. So that's one other thing to look into, one other tool to use. Another thing is that you can use is just file and just do main. This is the most simplest one, but it will tell you like it's an executable and the architecture that it was built for. Now, what can I do here? So like, just to show you here, like, no. Okay, so we have, I'm trying to find Safari here. Okay, so safari.app. And the contents here, Mac OS. And this is the executable. I can come here and then just do O2-L. And so that's some information. I think right now, because actually not so sure why this is a smaller size here of the binary. That's probably, I have to look into that. But as for my main app here, main app here. So the O2 we showed, NM we showed, strict we showed. Your real app, you have to go and look into that for your in your report navigator, build. You can go and search for that. There are two ways to search in the report navigator. I wish somebody told me this ages ago. You can search for here and you can search for like mkdir. Nothing shows up. Okay. Now I can also do Command F, which is this other thing, and it searches differently. Like this is more low level. Like you can search everything through this. So if I just like go here, I can search all of that. This sort of filter here is only for this like human understandable way. If I search for like right here, then I can search for it. Now, the other thing like you want to see is like I can search for Clang, nothing. But then if I search for like compile, the human way of it, compile auth, and then if I expand on this, you would actually see that it's using Swift front end here. Now, the other thing that you might want to also search for is like strip. No stripping is happening. Now, if the stripping is also affected by the configuration that you're building for. Like if you build in release mode, then it will want to do that stripping for you. If you're doing it in debug mode, it's going to be like, you just want this build to be, you want to run the app immediately. I'm not going to spend time on stripping that for you. There are different objectives between release mode and debug mode. Like just to show you like some of the other differences here. You search for either like strip. Okay, so actually dwarf. When you're doing active development and debugging, then the debug information format is just set to dwarf. When you're doing a release mode, it's step 2 with dsims. And part of that is you have to link all of your debug information into a single binary itself. And that takes time. You don't want to spend that time. You just want to use the debug information, which is scattered around in all your object files. So that's one thing. Debug intends to be faster. Another thing that you also want to look for is this here. So here, optimization level, what this does is it doesn't do any optimizations. it's not gonna necessarily be fast, but then it allows you to tweak and like do those stepping in, do those breakpoints, do those backtracing and all that. If you set it to release, then you're not capable of doing some of those. If you're not able to do some of those like debugger things, but then you also get some benefits of, I can move this zoom setting. You get some extra functionality from, you get some, trying to find the right word. You get some extra speed because Xcode didn't put in some extra checks when your app is actually running. Right, so moving away from here, and I have to go back to the slides. I'm going to stop sharing. All right, so about the DSIMs, one other thing is that affects the UID of your binary and your DSIM is the build tool version that you're using. So if you're using a different version of Xcode, then the UID of your DSIM and your binary won't match. If there's a code change, it obviously won't match. And if you changed any build setting like that, any of those build settings that we discussed, then the UID would be different. Even if you didn't change your Xcode version or you didn't change your code change, any changes in code, it'll be different. But after you strip, the UID would be the same, which is what you want. So UID doesn't match, then you can't symbolicate. Right, so moving on to the next slide. We already did the demo of all of these. Now, which build setting matters? It depends on where the compilation is happening and where you're doing your stripping. For example, if you're using CocoaPods, then if you have a pod file, then it still doesn't mean that everything is getting compiled in your main repo. It could be that the settings in your pod file are what governs it and overriding things. For a given framework, you could also pre-compile it. All right, let me. Okay, so let me start over. The build settings matters, and sometimes you have build settings in your main app, and that's sort of like in your project, and that sort of affects other things. If you have a pod, then you're doing the compilation in your like main app, like you pulled your pod into your main app, then the pod file, those the settings of the pod file matter. And if you're doing an XC framework and you're pre-compiling things from before, then the build settings of what you're doing before, and then you're dragging in the pre-compiled binary into your app, that's what matters. Now, this is tricky because, oops, this user here, there's a CocoaPods issue where they are not stripping your binaries correctly because of one setting, and I have to copy that. Just give me 1 second. Sorry about that. So Xcode, it's incorrectly setting this strip install product, which means that it's not going to strip each and every one of your frameworks. So this is Jordan Rose, which is an Apple engineer, and he said, we didn't strip, because the stripping was done incorrectly, then they added an extra 9 megabytes for a single framework. Now imagine if you have like 10 different frameworks, then that could be potentially 10 times 10 times 9, and that's like 90 megabytes that you've added bloat to your application. So try to wrap this up. Let me go back to here. Why saving space matters? Well, this is from Russ Shanahan, and he has an app. It's just 36 megabytes. I'm not sharing, sorry. So his app was actually 36 megabytes. And he says sometimes in his logs, he is seeing that some customers, they don't have enough space even for this app. Or sometimes the OS itself, even though you have more than a gigabyte of space, it'll fail you because there are lots and lots of other apps that are running in the background. And also, like if you can bring your app below the 200 megabytes threshold, then your app can also be installed over cellular data. So a recap of everything that we discussed, a lot more happens than just compiling code. Like there's stripping, there's linking, there's generation of the DSIMs. You can always try simple things with the Swift compiler and LD. Look into the build logs. Understanding static versus dynamic linking is key, and it helps you where to look for things. Understanding the command line tools is 10x more important than understanding the GUI. A little bit emphasized on that again. Don't substitute build tools easily. Like CocoaPods, there's an issue with. There could be issues with it. Carthage, there's been issues with it. Even Apple themselves, when they have this new version of Xcode, sometimes they have issues within it. Apple has an abundant amount of good resources. They're a bit scattered, but you have to look for them. Things that affect app size are the amount of source code, the way that you link, optimizations that you select, the stripping, if it's done correctly or not, the number of assets and their size and format. We didn't discuss this, but these are covered in other Apple resources. Having on-demand resources, the kind of platform that you're building for, the architecture that you're building for. And also one other thing is Apple says if you're trying to create reports, then your report should be on the App Store builds itself, which you can find that from App Store Connect. The reason for that is after you build and sign your app, Apple does an extra signing on it for the DRM, and that adds extra sizing to your app. Every setting creates a new branch, a new possibility of how you're compiling things. And last but not least, you can inspect binaries using NM, old tool. And one other way of testing things is just like, let me go and try to strip this framework in my app and see what the effect of that is. If I am stripping this app and I see significant file size change, then that means that something is being done wrong. For example, I have this ls. So I have this, my original framework is 18,400. This is just one framework, okay?
Can you switch over?
I'm not sharing again, I bet. Right, so ls-la. I have, this is the original framework, and this is a bad, this is the original framework. Just ignore the bad, let me just actually remove that. Okay. All right, so it's 18 megabytes. Okay. Now I can do nm-a, original framework, and then I'm going to do a grep for debug symbols, which I can just do by this. That's for debug symbols. And I'm going to get you the number of lines that have debug symbols. 124,000. I'm going to do the same thing, but I'm going to grep for Swift symbols, which are written. You also don't need them. Now, and just to show you like the total number of symbols that I have, 168,000. This is just one framework. Now I'm going to strip this framework. Okay, now do LSA, highlight, and it's down to 6.7. If I do, again, the same thing here, the number of debug symbols is now just 1. If I do, what is it? Again, the number of Swift symbols are now reduced from 86,000 down to 21. So like, this is one way for you to go and check, like just try attempting stripping and see what the effect of that is on your framework. If you see significant change, then that means something in your whole build process is being done incorrectly. All right. And you can also use the file, which you already discussed. Some shout outs, special thanks to 2 of my colleagues, which they were doing some initial dev work, and then I was able to pick up through that. Mark Rowe, which is engineer at Google, he helped answering some of my questions, and Sagarja as well. Some references. These are some of the WWC videos, link fast and behind the scenes of Xcode build process. I've probably watched 7 or 8 times each and every one of these videos. There's a gigantic amount of information in those videos. Everybody should definitely watch them. And yes, thank you all.
Thank you. I have 2 questions I'll ask from the chat right away, both from Ed. So the first one is, I think back when we were talking about bundling, what about bundling multi-platform libraries, such as things for the device and simulator? I think how's that handled in terms of, I think when it generates the frameworks?
I don't think I don't think having multiple frameworks is an issue, because as long as you strip them correctly, then everything is done correctly. It should be done correctly. You have tools to validate that, so just try and do that. Like more or less, what you're describing is like an X3 framework, which you're building for a simulator, and you're also building your framework for the real device. For both of these, if your settings are done correctly, then everything should work.
Okay, and then he also asked, can you get symbolicated crash reports from a stripped binary?
From what?
Stripped binary.
Yes and no. Okay. If you strip it, then if your OS has the DSIMs, like right now, if I crash an app and strip it, if I have the same DSIM on my OS, then as soon as your crash is generated, the OS actually hooks into that DSIM and it symbolicates it immediately for you. But on a real device, like on a customer's device, the DSIM is not on that device. The DSIM is actually like 10 times more, usually bigger than the actual app itself. Like if we, in the sample that I did, like the actual binary of the app in this command line example was actually just 56 kilobytes. So the DSIM of that is like 1.8 megabytes of size.
Any other questions?
Yeah.
Is this going to be recorded? We can see this later.
Yeah, it is recorded. We'll have it up on our YouTube page probably in a few weeks.
Any difference between Swift Package Manager and CocoaPods as far as size?
I don't have SPM experience, but my guess is, how do you create a framework? And it all comes down to your source code and the flags that are being passed to it. CocoaPods is, the way you have to think of it is, it's a helper tool that you go in, like, instead of like me going in like changing every setting for every like target that I have, what I can instead do is like have them change in one pod file. With SVM, I think like the manifest file, I think, like it sort of has like some instructions for like how what flags you want passed on to it. But as long as like those flags are correct, then everything should work. The one thing, I actually opened a DTS ticket to like ask some questions answered by Apple. And the one thing that Apple suggested was that don't try to rely on like third-party build tools, because they affect the build settings, and you may not know of it. The best way to be sure that everything is working as expected is go and try to create something from scratch. create an SVM from scratch, create a dynamic library from scratch, and then see the default settings that Xcode has for those, and as long as those are like, try to see the default settings, and then see if everything matches with the default settings that you have.
So did you get to solve the mystery of why your app grew in size after the move to XC frameworks, or have you had a chance to explore
Did
that?
not. However, like, we found other issues elsewhere. And those other issues elsewhere were like much more significant than the issue that we saw initially.
What's that feeling?
Yeah.
Yeah. I know I stumbled on that CocoaPods issue after we updated Xcode 14, because I think that's when it really became prevalent, the strip one. I think
Oh, really? Okay.
it became problematic after Xcode 14, is I think even when they found it in open source. Because Xcode 14 already blew a lot of things size-wise out of the water. Okay, any other questions? Right, let me go back to wrap up then quickly, and then. All right, so I think once again, I will send all these links out through the Meetup page. I'll send them out as a message to the event. But if you're interested in speaking, the speaker form is there. Again, we will accept both in-person and virtual speakers, and depending on how we have talks slotted, we could theoretically do 2 in a meetup. If you want to catch this video, they will be on the Dev Community YouTube channel, as long as some recordings from our other groups. I believe there should be some iOS Soho videos coming soon, and DC Android is actually getting ready to restart as well, so maybe keep an eye out. Eventually there'll be some Android videos. We do have a Slack workspace. As I said, it's not super active, but perhaps you can help rejuvenate it if you're interested. And we do have a Mastodon account now, and for the people here in person, I have some stickers as usual afterwards. Next month, we'll be back at Capital One. I don't know our room yet. I think it will kind of depend on some of the AV situations. Based on the timing, I'm intending we'll probably have a lightning talk session, so it'll be just some quick lightning talks. Maybe I'll look for like 3 to 5 speakers who are interested. We'll do some quick lightning talks based off our what we saw at Dub, and then we'll go back to regular speakers in July. And with that, thank you everyone for coming, and hope you had a good night.